Welcome to today's explainer. We're going to completely ditch the hype around magical, self-organizing AI swarms today and replace it with something way more useful: deterministic, scalable software engineering. If you're an engineer or architect trying to get AI to actually work reliably in production, well, you're absolutely in the right place.
Let's quickly map out our blueprint. We'll start by breaking down the mega agent trap, look at how to build an AI org chart, and then dive into 4 precise multi-agent design patterns used in production right now: the sequential assembly line, router dispatch, parallel fanouts, and finally, the hierarchical manager.
All right, Section 1, the mega agent trap. We literally have to start by addressing the elephant in the code base, the way almost every developer first tries to build an agent.
I want you to think about your own repos for a second. Think about those initial attempts to deploy an autonomous agent. Why do those prototypes so often hit an absolute brick wall of unreliability the second they touch real user data?
Well, this exposes what we call the monolithic mega agent trap. In his book, Patterns for Building AI Agents, Sam Bhagwat points out a classic anti-pattern. Developers take a single model and they just stuff a massive system prompt with like 50 different tools. The problem? The likelihood of your agent completely failing and picking the wrong tool goes up exponentially with the number of tools you give it. It gets confused, it hallucinates, it gets stuck in these infinite execution loops, and honestly, the worst part, it acts as a black box that is practically impossible to debug.
Moving to Section 2, building the org chart. Because the way we fix this massive failure rate is by completely shifting our mindset toward organizational design.
The crucial point here is that we have got to stop thinking about AI as this magic, omnipotent brain. Instead, we need to treat it like a human corporate org chart, modeled directly in code. We have to rely on those tried-and-true divide-and-conquer principles. The contrast here is pretty stark. Instead of one overloaded black box just failing constantly, you architect a system of narrow, highly specialized sub-agents. You give each sub-agent maybe 2 or maybe 3 specific tools, crystal clear instructions, and you manage the whole thing with deterministic software workflows. And hey, this isn't just theory. Anthropic's internal research shows that by using targeted agents with discrete tool sets, these multi-agent systems actually outperform single generalist agents by over 90% on complex tasks. Over 90%. That is a massive leap in reliability. So how do we actually build this thing?
That brings us to Section 3, the sequential assembly line. Let's look at the first and honestly most foundational of our 4 multi-agent patterns.
This one is exactly what it sounds like: a predetermined control flow. It's highly deterministic, which means it's incredibly easy to debug. Because it moves strictly step by step, you get a crystal clear audit trail. You know exactly where the data came from at every single stage of execution.
Think of it like an assembly line for content. Imagine a coordinator agent that reads a massive product brief and just extracts the key bullet points. It then hands those bullets off to a LinkedIn agent whose only job is writing professional posts. Then, that output gets passed down the line to a social agent configured strictly for short, punchy tweets.
When you map out a product marketing request flowing through this kind of pipeline, you see the coordinator extracting info first. Every single task is perfectly isolated. No single agent gets overwhelmed. But, as your system scales up, a purely linear sequence isn't always going to cut it.
Which leads us to Section 4, the router dispatch pattern, because as we scale, we definitely need a way to handle dynamic user intent.
The router pattern acts as a deterministic dispatch layer. It protects your user from needing to know which specific agent to talk to. They just submit a request, and a routing layer analyzes it and sends it to the right place. And honestly, here's the best secret. That router doesn't even always need to be AI. Sometimes a rock-solid Python if-else statement tied to a drop-down menu is literally the best router you can build.
By handling all that routing complexity up front, your downstream agents get to stay hyper-focused. They receive a narrowly defined intent, they grab their 2 or 3 specific tools, and they just execute. This drastically cuts down on the risk of hallucinations, simply because the model isn't trying to juggle a bunch of totally unrelated contexts. So in practice, a coordinator adds some context and hands the task off to a router, which instantly fires it over to the exact specialist needed, whether that's a LinkedIn, social, or blog agent. You are completely sidestepping the trap of building a master agent that tries and usually fails to write mediocre versions of everything. All right, Section 5, parallel fanout workflows. Let's look at what happens when we need raw speed and diverse perspectives all at the same time, rather than just doing one task after another.
Parallel workflows look a lot like the classic fan-out, fan-in cloud design pattern. This is absolutely perfect for something like an automated pull request review system. You have the router spawn 3 agents at once. One checks for security vulnerabilities, one checks code style, and a third runs performance checks. They're all working simultaneously, and then a final synthesizer agent merges their notes into one clean, consolidated report.
But there's a pretty massive hidden danger here. Parallel workflows are incredibly fragile if they lack shared context. If subagent 1 and subagent 2 are executing in parallel, but they are totally unaware of each other's work or the broader system state, they might spit out completely conflicting logic. The final synthesizer agent at the bottom is then forced to try and mash together totally incompatible data, which usually ends in a system crash or a wildly hallucinated output.
To fix this, you've got to carefully engineer your architecture to preserve a continuous, consistent context string across all those subtasks. That synthesizer agent absolutely needs that shared context passed along with the work so it can accurately combine the results without failing. It's basically a critical software engineering constraint applied directly to prompt engineering.
And finally, Section 6, the Hierarchical Manager Pattern. This is the highest level of abstraction, completely reserved for the most complex, open-ended problems your software is going to face.
This pattern literally mimics corporate middle management. A supervisor agent gets a massive goal, say researching an entire market landscape. It breaks that goal down into distinct subtasks, delegates those out to specialized worker agents, waits for the output, and critically, it reviews their work. If the output isn't up to par, the manager kicks it right back to the worker. It maintains a very strict chain of responsibility.
Pulling straight from Anthropic's internal decision framework, this matrix shows exactly how you should map your software requirements to the right multi-agent org chart. Doing routine analysis? Stick to a single agent. Got predictable multi-domain tasks? Use sequential or parallel workflows. And for that really complex, open-ended research, bring in the hierarchical manager. Following this prevents you from making the super costly mistake of over-engineering a massive swarm when a simple sequential pipeline would have nailed it.
So I want to leave you with this question to chew on. Challenge yourself to really look at your current AI code bases. Are you genuinely building deterministic, scalable software architectures, or are you just throwing 50 tools into a massive system prompt and praying a magic swarm figures it out? Divide and conquer, use these patterns, and build real multi-agent organizational structures. Thanks for hanging out with me on this explainer, and I'll catch you in the next one.